There are several methods to determine the convergence of an infinite series. Today, let's explore two fundamental approaches. An infinite series is expressed as the sum of an infinite number of terms. The sum of the first n terms is referred to as the nth partial sum. Let's denote this partial sum as Sn. If Sn converges, the infinite series converges. And if Sn diverges, the infinite series also diverges. Let's consider an example. The infinite series of 1 over 2 to the power of n. The partial sum, denoted as Sn, this can be calculated using the sum of a geometric series formula. It can be simplified as 2n minus 1 over 2n. The limit of Sn. As n approaches infinity, the partial sum converges to 1. Therefore, as initially mentioned, since the partial sum converges, the infinite series itself converges, and the sum of the infinite series is 1. The sum of this infinite series can also be calculated as this. This aligns with the concept of the sum of an infinite geometric series that we learned in pre-calculus. Now let's reconsider this infinite geometric series. An infinite geometric series diverges when the absolute value of the common ratio, denoted as r, is greater than or equal to 1. If the absolute value of r is greater than 0 and less than 1, the series converges, and its sum is given by a over 1 minus r. Let's represent the repeating decimal 0.1313 as a geometric series and express its sum as a ratio of two integers. The repeating decimal can be expressed as a geometric series, where the first term is 0.13 and the common ratio r is 0.01. As the common ratio satisfies the convergence condition, the sum of this infinite geometric series is 0.13 over 1 minus 0.01 equals 0.13 over 0.99. It can be simplified as 13 over 99. Now, let's explore the nth term test for divergence, a method used to determine divergence. It is well known that if an infinite series converges, the limit of its nth term is 0. Let's briefly examine the proof process. Assume that an infinite series converges, and its sum is denoted as L. The partial sum up to the nth term can be expressed as follows: Sn equals Sn minus 1 plus An, where An represents the nth term. The sum L of this infinite series is the limit of Sn. By substituting Sn minus 1 plus An for Sn, the limit of the partial sum can be expressed as the sum of the limits of the partial sum and the nth term. Since the limit of Sn minus 1 is equal to the limit of Sn, which is L, the limit of the nth term ultimately becomes 0. In practical terms, the proposition that is more frequently used in determining the convergence divergence of an infinite series is the contrapositive. The contrapositive states that if the limit of the nth term is not 0, then the infinite series diverges. Let's use the proposition to determine the convergence or divergence of the following examples. The first infinite series is an infinite geometric series. Given that the common ratio r is greater than 1, the series diverges. The second infinite series has the nth term with a limit of 1/2. As the limit is not 0, this infinite series diverges. The third infinite series, as observed from the graph, the limit is not 0, therefore, this infinite series also diverges. For the fourth infinite series, the nth term has a limit of 0. In such cases, we cannot determine convergence or divergence. We will study this further in the next session when we delve into the integral test and convergence of p-series. See you next time!